Now let's talk about what I think is one of the most exciting features in modern Fortran, which is that Fortran is now the only mainstream scientific programming language that has a parallel programming model built into the language that scales all the way from single socket multi-core chips out to and beyond 100,000 cores on massively parallel supercomputers. The primary parallel programming feature in modern Fortran is called coarrays. And with coarrays, the user has explicit control over the distribution of data and explicit ability to communicate data in a one-sided manner, where one process can go out and grab data from another or put data into another process. What happens with coarray code in Fortran as of the Fortran 2008 standard is that the compiler sets up for the program to start up as multiple replications of itself, each having the same code, not necessarily each taking the same path through the code, because there could be conditionals that could change the path through the code. And each program then, each image then goes along on its merry way until it encounters some form of synchronization. That could be a statement like a sync all that would be replicated across all of the images. And only at that point do the images actually synchronize with each other. Synchronizations also happen when there's a memory allocation or deallocation. And the coarrays define what's referred to as a partitioned global address space. So Fortran falls into the category of PGAS languages. So let's see the way the partitioning works. Here I'm using the colon notation that's been in Fortran since the Fortran 90 standard, where 1:4 is referring to 4 elements of an array, and we can operate on those 4 elements as a block of data at once. Those elements are in regular parentheses, and because they're a regular dimension of the array. Now with coarrays, you can also have one or more codimensions that are listed in square braces. And when a program ranges over the regular dimensions, the user is, or the image is operating on its own local data. And when the codimension varies, the image is potentially doing communication to operate on global data across the program. Here's one example of how the coarray mechanism is used to do communication. Let's say each image is executing this line. What's happening then is that we're copying data from image 2, copying element 1 from image 2 to element 1 of image 1 when this line executes. When image 2 executes the same line, basically it's copying data onto itself, which the compiler might optimize away or which you might just get rid of with a conditional statement. When, say, the nth image executes the same line, it's copying that same element to element 1 on that image. Notice that I don't show square braces on the left-hand side because they can be implicit. When you don't show square braces, you're only working on the local data. Now let's look at a more fine-grained and implicit form of parallelism that's built into Fortran since the Fortran 2008 standard, which was actually published in 2010. It's referred to as do concurrent. And let's imagine that we're going to approximate the derivative of a real function sampled at n points. And we have one array holding the approximations to the derivative and a second array holding the function itself. And the endpoints are spaced a distance dx apart. We'll imagine that somewhere in between the declaration and the do concurrent, we initialize the data. And when we write do concurrent, it at first looks like a serial looping construct, like a regular do loop. But in fact, what we're doing is we're communicating to the compiler that there are no data dependencies between the different iterations through this do concurrent construct. So we're going to grab a point to the right of where we're calculating the derivative and subtract off a point to the left. So we're using a simple central difference approximation here. And then divide by twice the grid spacing. What's significant about the do concurrent construct is that it enables us to communicate to the compiler the opportunity for concurrency, but allowing the compiler to decide how to exploit that opportunity, or possibly to not exploit it at all. Depending on the hardware that's available or the compiler that you're using, you might end up with vectorization. You might end up with multi-threading. And the best part about not specifying it is that it could vary as you move from one platform to the next, but more importantly, the compiler could decide not to actually issue any sort of parallel instruction if the overhead of launching the parallel instructions is higher than the benefit that would be gained based on the amount of work that's going to be done. So this demonstrates one of the core philosophies of the Fortran language, which is to enable the programmer to communicate properties of the code, not specific optimizations. In addition to the fact that the compiler could choose different optimizations based on the available hardware, the compiler is also free to ignore these opportunities in cases where the overhead incurred from exploiting the parallelism might not be justified based on the amount of work that's being done. Some of the features of modern Fortran that make it unique are that it's standardized. So other parallel programming languages, for the most part, are not, at least those that scale to massively parallel platforms, but also that it's widely available. And this is actually a little known fact. There are mainstream compilers. Right now, the first two are the Cray and the Intel compilers that support all of the features that we've talked about, so that many users already have this parallel programming model in their hands in commercially released compilers. And most importantly, that it's scalable. It can work on a laptop or on a massively parallel supercomputer.